Okay, I think it's working now. Okay, so if you remember, if you were here in our last lecture, I defined a system. Okay, so I have a problem here. The pen doesn't write where I touch. So that's because the screen resolution has changed. So let me try to fix that. Okay, let me see. Okay, so I said a system can be defined in many different ways, and system is a very common word, right? I'm sure every one of you has heard the word system before, and it's hard to make a definition for that, and what I'm defining here may not be true for anywhere else. So remember, so everything I'm saying is specific to this course and in controls, specific controls engineering is in general. So for something to be called a system, there needs to be some inputs to that, and then there needs to be some outputs coming out of that system. And so as an example, if you consider an aircraft, the inputs can be the control inputs the pilot can give in the cockpit, and these include the control surface deflections, the elevator control, aileron control, rudder control, and we can add some more things here. And the output can be the physical variable that represents the motion of the aircraft, and the speed of the aircraft can be, for example, one of them, or its altitude, and you can add more stuff there. Okay, so what I wrote here corresponds to some physical quantities, right? For example, if you consider this, that's the elevator deflection angle. So if you are controlling an aircraft, you know that there's a tail surface, and at the trailing edge of the tail, there's a control surface, and by controlling the deflection of that, we can control the motion of our aircraft. For example, if you consider this, the angle here is our elevator deflection angle. Okay, so this is one of our inputs, delta elevator, and this is an angle. It can be radians or it can be degrees. And for example, the speed of the aircraft, that's another physical quantity, and that will have the units of speed, right? For example, we use meters per second as a unit for speed. Okay, so the elevator deflection is an angle, and let's say the elevator is equal to the elevator is equal to 10 degrees, or let me use something more relevant, and let's use the throttle, for example, delta throttle. Let's say this is set at 50%. And speed of the aircraft is, I don't know, let's let that be 200 meters per second. So what's more important than the instantaneous values of these input and output, we care more about their history, their time history. So this single value itself, that shows the input we're giving to the system at that moment. But as I said, what's more important is the variation of that input within a certain time frame. So we consider a time interval starting from some initial value, and okay, so let this be our inputs. And this now graph shows how much input has changed in a certain time interval. So now this has become an signal, right? So this has become a function of time. Similarly, rather than the value of the output at a single time instant, what is more useful is how it changes as a function of time. So let this represent so I'm drawing these all randomly, obviously. So this shows how much the speed of the aircraft changed as a function of time. By the way, you don't have to write these down as well, because I will give you these files as well. I mean, if you want, you're obviously welcome to take notes. Their histories, so inputs and output of systems are represented as functions of time. In other words, they are signals. Okay? So this is an extra information. I didn't say these things last year, so hopefully these will help you understand it better. Okay, now let me go back to the okay, today I would like to talk about classifications of systems. Even though in this class we will be considering a particular class of systems only, at the beginning I think it's useful for you to know the general types of systems. So let's start with that topic, classification of systems. Okay, so there are different ways you can classify a system. So I will show you several of them, and this is not the complete list of classifications. You can classify this is a system with respect to some other properties as well. But I start with this: static versus dynamic systems. So this classification divides the entire set of systems into two. So what I mean is, any system has to be within either one of these categories. A system is either a static system or a dynamic system. So there's no other way. So any system you think of should be one of these two. So we divide the entire systems into two groups. Okay, so a system is said to be static if its output depends upon the present input only. If the output depends on present and past input values, then it is called a dynamic system. So this is how we distinguish dynamic systems from static systems. Okay, so let's start from a similar example that you will all know. Suppose that we have a car, okay, and maybe I should start from here. So we have gas pedal inputs, and then we have brakes. So we only consider controlling the speed of the car, and the output is the speed. Okay, so our car is initially at rest. Okay, so the input is the gas pedal, and the value of input at t is equal to 0 is 0. So the car is not moving, and the output, this is v of t, it's at 0, right? Initially, when time is 0, the speed of the car is 0. Suppose that we step on the gas pedal and we start giving an input of a certain amount of gas pedal, right? So let this be, I don't know, 50%. So we step on halfway through the gas pedal, and as you will all know, the car will start accelerating, right? The speed of the car will start increasing, and then after a certain while it will reach a constant speed if the road is level. Okay, suppose that is the case, and the speed of the car changes until it reaches a steady state speed. Okay, so now let me ask you this question: do you think this system is a static system or a dynamic system? I heard dynamic, right? And somebody says static. Okay, so it's really very easy to distinguish if you go back to the definition and think about what it says. The definition says a system is static if its output depends upon the present input only. Now let's check. Okay, so suppose that we freeze the time at this instant. Let me call this T1. And at that instant T1, the car has a specific speed, which is V at T1. And the input at T1 is somewhere here. Let this be T1. And the input is set at, let me call it 0.5, which means the gas pedal is depressed halfway. Okay, so if you consider another time instant, let me choose this one, call this T2. If you look at T2, the input at T2 is still the same. We still apply the same input. Whereas if you look at the output is now different. The speed of the car at time T2 is something different than the speed of the car at T1. So this means this is a dynamic system, because the input didn't change, but the output changed. Okay, so the input, in other words, the output does not only depend on the input value at this instant, but it also depends on the previously applied input values. Okay, so if the pedal was not depressed at this value during all this time, the car wouldn't be at that speed. Does that make sense? So this means this is a dynamic system. Okay, so there was another example here, so let's go back to this one. So this is just a mathematical system. So we only know this mathematical relation. So I don't know if this corresponds to any physical system or not. Well, that may be an amplifier, I guess. Okay, so in that example, the input-output relation is given by bilgisayarı tam ısınamadı hala. Bunlar çıkartıyor. And for this system, we are given this mathematical relation which relates the input to the output, and it is just this simple equation. Whatever input we apply, the output is just 2 times of that. So if you consider the previous inputs, we start giving a constant input, then the output will be just twice that, right? So now this is a static system. If whatever value of the input is, the output is just 2 times that. So if any instant we change the input, let me use a different color. So suppose that at any instant we change the input from 0.5 to 0.75, the output will change at the same instant from 1 to twice that input, which is 1.5. Okay, so if you consider this time instant, for example, let's consider this time t2. The output of the system is 1.5 here, and that value depends on the input applied at that moment only. And the output is 1.5 because the input at that time is 0.75. And whatever input was applied prior to that time instant has no effect on the output. So what I mean is the input history may have been something like some total random inputs. The output for that ne oldu? So as long as the value of the input at that instant is 0.75, the output will always be 1.5. Okay, so I think this is enough about static versus dynamic systems. But again, so you should really keep these definitions in mind. As long as you remember the definition, it's very easy to understand what type of system you have. Okay, so I can tell you at this point that if you just have the mathematical equation for a system, you can easily see if your system is static or dynamic by just looking at that equation. The system equations for static systems are always non-differential equations, which is the case in this last example, right? This is a non-differential equation, obviously. There are no derivative terms or there are no integral terms. So without doing anything, you can immediately say that you have a static system by just looking at the equation. Okay, so let's move on to the next. Okay, so there was this example in the notes, so maybe I can very quickly talk about that. So this is a dynamic system. This time we have this integrator system. So the relation between the input and output is that the output is the time integral of the input. So this is our system equation. And if you consider the system, you can immediately see that this is a dynamic system as well. And in this case, first we consider this input. We start giving an input to the system at this instant. And the output will be integral of that, right? The output will be the area under that input, which obviously grows in time. So this is the output. And if you consider a second input, which is this dashed line, and the second input is also a constant input, but it starts at a different time instant. And now the integral for the second input will be started from this instant. Okay? So again, if you consider these two inputs, and at this time instant, they are both the same. Both U1 and U2 have the same value, but the outputs are different for those two input signals. For the first one, the output is here, but the second one, the output is here. So this also means that we have a dynamic system, because the output doesn't depend on the current value of the input only. It also depends on the previously applied inputs. Okay, so this was one way to classify systems. Another way is to classify systems with respect to their time variance property. Again, this classification divides the systems into two, but obviously we divide it in a different way. We divide it based on a different property. Just like in the previous case, any system has to be either a time varying system or a time invariant system. So there's no other way. So every system should be in one of these two categories. So let's read the definition. A system is time invariant if the time shift in the input signal results in corresponding time shift in the output. So mathematically you can show it like this. So by the way, the notes are not very clear, but hopefully you can read it. So we have an input signal, U, as a function of time, and this creates an output which is another function of time. So if a system is time invariant, then this should be true. If you shift the input in time, that is, instead of U as a function of time, you apply the input as U as a function of t minus some capital T. So this capital T is the time shift. Then the response of the system should be shifted by the same amount. Okay, so let's suppose that you have an input and that creates an output, right? Remember, this can be the car accelerating problem from before. So the car starts accelerating. So so this black one is U T. Now let's consider that we shift this input by a certain amount. Let's say we shift it by capital T seconds. That means we move the signal to the left or to the right. Okay, so this red one is now U T minus capital T, where capital T is this time shift. Okay, if the output is shifted by the same amount, let me make up some room. Bu böyle tahta yazmaya göre çok daha güzel bir şey ya. Tahtada bunun hiçbirisini yapamıyorsun ya. Bir de tahtayı silmek zorunda kalmıyorsun. Senin de çok pis bir iş o. Okay, so this is the output. If the output is shifted by the same amount, şimdi bak bunu tahta nasıl yapacaksın? Now this should be the same amount, capital T. So you know that the outputs are the same. And if this is true for all capital T values, then we have a time invariant system. Or on the opposite side, if the response is different when you shift the input, you give the same input but you get a different response. So how can it be? For example, the output is something like so this is so this is time invariant. If you get a different response, such as this one, for example, you give the input at a different time, but you get somehow a different response. So obviously the green response is different than the green output is different than the black output, right? So this means this should correspond to a time varying system. Okay. So now let me give you an example of a time varying system from real life. So we talked about this car accelerating problem. Do you think that's a time varying system or a time invariant system? Well, it's actually difficult to answer that question. If you are too precise, then you can claim that a car is a time varying system. For example, remember this example? You step on the gas and your car starts accelerating, right? This black one. If you do this in the summer, you step on the gas and the car will accelerate. You will get a response, you will get an output. And if you do that in the winter, you will get slightly different response. The performance of the car will not be the same, right? So the response, it will not be too different, but if you look at very close look at the output, you will see some slight changes. So in that sense, you may say that your car is a time varying system because it depends on you get different responses. But obviously, what's important there is not really the time. In that case, the important parameter is the output temperature. But still, time is an important factor because the car gets old, right? So if you have a brand new car, you will get a certain response. But if you drive the car for, I don't know, 10 years, and after 10 years, you'll get a different performance because the internal mechanics of the car will be different. But that's not a very big change. So for most of practical purposes, you can assume that to be a time invariant system. Let me give you another example where the system is significantly time varying, and that is a missile, for example. If you consider a missile, suppose that you have an air defense system. Suppose that you have a missile here, and now you fire it, right? So this goes and tries to hit some target. Suppose that you have an enemy aircraft approaching, and you want to hit that. So this missile starts from rest. It is at launcher. It's not moving. And as soon as you fire it, it starts accelerating, right? So there's a rocket here. That rocket will start accelerating the missile. And then there will be some significant changes in the properties of the missile. For example, initially you have almost, I don't know, half of the missile rocket propellant here. So the missile weighs, let's say, 1,000 kilograms at first, but when it comes here, the mass of the missile is, let's say, 500 kilograms, because the half of the missile was propellant and it's consumed. And obviously its other mass properties change as well. Its moment of inertia value is different. Its speed is different, right? So here the speed is 0, and let's say at this point its speed may be I don't know, 1,000 meters per second. So that means the aerodynamic forces will be very different. So here there are no aerodynamic forces because the dynamic pressure is 0. But here you have a huge dynamic pressure, 102 v squared. So that means if you deflect your elevator here, there will be no output because the speed is 0. The control surface deflection will create no response. But if you do it here, under these conditions, you will get a very different response. And anywhere in the middle, the response constantly changes. So this is obviously a time-varying system because so this is the elevator. Suppose that you give this much of elevator deflection. And as the output, let's consider the acceleration of the missile, the acceleration in z direction. So you get no response. Because the dynamic pressure is 0. But if you apply the same input at, I don't know, let's say 5 seconds later, so this is 5 seconds, then this time you get a huge response because you have a huge dynamic pressure you will get. So let me now write everything I just said. So let me just summarize that. Is obviously an time-varying system. Both mass properties are bu cümleyi bakın toparlayabilecek miyim? Giving the same input later in time results in an output that is different than the output corresponding to the same input applied earlier. Oldu değil mi? Okay, I guess you understand what I mean. Okay, so this is how you distinguish a time-varying system from a time-invariant system. Okay, so this is just the same thing, so you can look at this. The next one is the linearity property. This is also a very important property. Suppose that we have this huge set of systems. And first we divided these systems into their static or dynamic properties. So that means we said that, so this is distinction. So we have static systems here and dynamic systems here. Next, we divide the system with respect to another property, the time variance property. So we still have the same systems, but now we divide them differently. So let's say we divide them like that, and then these were time varying and time invariant. Next, we have the linearity property. But before I start talking about that, let's give a break and let's continue after 10 minutes, okay?